Hi there. In this video, we're going to continue on with Chapter 3 in the second of our applications of derivatives when trying to understand graphs of functions. And this one's titled the mean value theorem, which is the main theorem in this section, but it's not the only theorem. So let's get started. So we're going to start with something called Rolle's theorem, another very old one. Very old theorem. And so the idea is that we start with a function that has three characteristics: continuous, differentiable, and the endpoints are equal. So let's go over what the qualifications for using Rolle's theorem entail. So continuous on a closed interval. That means no vertical asymptotes. Differentiable on the open interval. We saw that in the previous section, that differentiability at the endpoints always fails. So we can't require that endpoints be differentiable. So it's just we're moving in one point. And then this theorem is about the endpoints, right? The endpoints, the y values have to be equal. If that happens, then that means that there is a number c in AB such that the derivative is 0. So continuous everywhere, differentiable everywhere, except the endpoints. And the endpoints are equal, then somewhere in there, we have a derivative equal to 0. So here's a few pictures that hopefully illustrate why this theorem is believable. So notice in all these pictures, the endpoints are equal. So the y coordinates. So f of a equals f of b. All of these are continuous. All of these are differentiable, except at the endpoints, obviously. And notice that all of them have the derivative equal to 0 somewhere. And just by looking at the graphs, it should convince you that this makes sense. Right? It has to do with continuity, right? There's no discontinuities. And the function can't change direction at a corner, right? So if the function is going to change direction, it has to change direction where the derivative equals 0. So we're using, stuff that we learned in section 3.1, right? Using Fermat's theorem and stuff like that. So here's the proof. So we're going to look at what happens when the function is a constant. Okay, so if f of x is a constant, then the endpoints are definitely equal. Constants are differentiable. And it's continuous, so it satisfies all three conditions. Right? And again, a constant is technically a polynomial. It's just a very small one. So the derivative of the whole thing is 0. Right? So it turns out that every number in the interval satisfies Rolle's theorem. Next, we want to look at what happens when somewhere on the interval there is any y value that is greater than the left endpoint. Okay? So that just means the function increases somewhere from the first point as it moves to the right. It moves up at some point in a continuous differentiable manner. What happens when that happens? What result do we get? Well, that just means that somewhere in the interval, there is a maximum. So I put these little, and you'll see this more and more as we progress through the semester. In the notes, if I put a little y, that means that you should look up why this is true. Okay? I'm not here to give you all of the answers, but I'm here to illustrate the type of reasoning you need to succeed in calculus. You should know why every statement is true. Unless I specifically say, we can't prove this, which I've done a couple of times, but not that much. So if the function increases anywhere to the right of the left endpoint, then that means there's a maximum somewhere. So we're just going to say that point, we're just going to call it c. So how do we know that the derivative has to equal 0 there? That's where we use Fermat's theorem. Okay, so that's why we proved that, right? Because we're using that to prove Rolle's theorem. We're actually going to use Rolle's theorem to prove the mean value theorem, which is used a lot in calculus. It's a very, very important result. All right. what happens in case 3 if f of x is less than f of a? Well, it turns out that's the opposite case. The opposite situation is case 2. I want you to try to prove that one on your own. Okay, so think about whether that would be true or false. Make sure you understand why there'd be in case 2. Make sure you understand why there's a maximum somewhere. You should be able to verify that. We've covered it. I want you to be able to recall all of these chains of reasoning. It's not logic, it's math. Math is not necessarily logic. We have to prove everything as we move along so that we can use it later. So that proves Rolle's theorem. And I'm going to show you how to use Rolle's theorem. So we're going to verify that this function satisfies the 3 hypotheses of Rolle's theorem on the interval given. And then we're going to find all numbers C that satisfy the conclusion of Rolle's theorem. So Rolle's theorem, continuous, differentiable, endpoints equal. Well, that's a polynomial, right? Polynomials are continuous and differentiable everywhere, except possibly the endpoints. I just put everywhere, because nothing's differentiable at an endpoint. Now we have to check that the endpoints are equal. So f of -1 is 11, f of 3 is 11. So that shows us that f of a equals f of b, and that's 11. So those are the 3 things we need to use Rolle's theorem. Continuous, differentiable, endpoints are equal. Now that the endpoints are equal, that means somewhere on the interval, the derivative is equal to 0. And we just need to take the derivative and set it equal to 0. So we have 4x minus 4 equals 0, so clearly x equals 1. That is the point that satisfies Rolle's theorem. So that's the type of thing you're going to have to do. Be fully prepared to do something like this on an exam. It might not look like this word for word, but you have to be able to use these general results that we've proved to determine, for example, if a function has this point or not. So continuous, differentiable, endpoints are equal, satisfies Rolle's theorem. So if there's a discontinuity, can't use Rolle's theorem. If somewhere it's not differentiable, if there's a corner, can't use Rolle's theorem. If the endpoints are not equal, can't use Rolle's theorem. Okay? Can only use it if all 3 of those are satisfied. All right, so now we're going to look at a more advanced use of Rolle's theorem. So we're going to use Rolle's theorem and the intermediate value theorem together to show that this equation has exactly 1 real root. So the term root means that the function crosses the x-axis. But what we're saying here is that it has 1 solution. So there's 1 value of x, exactly 1 value of x, that makes this true without graphing it. Remember, a graph is not a proof. Right? How do we know that there's not a hole in the graph where it looks like it crosses the x-axis? Right? So a graph is not a proof. A graph can be strong evidence or give us a reason to believe something is true. We need to do a proof here. So first thing we want to do is use Rolle's theorem, and then later we're going to use the intermediate value theorem. So this is a pretty long example. You have some stuff on the homework like this, but the version I'm going over here is what you're going to have to do on a test or something similar to this. So here's our strategy. We're going to assume the equation has 2 distinct roots and use Rolle's theorem to gain a contradiction. So let's go back and look at the problem again so we know what we're doing. We want to show there's exactly 1 real root. Okay? So we're going to assume it has 2. We're going to assume it crosses the x-axis twice. And we're going to show that Rolle's theorem shows us that this is impossible. So statement number 1. The function is continuous and differentiable everywhere on its domain except possibly endpoints, right? I'm just not even going to write that. Just assume that that's true. It saves me a little writing. So why is this continuous and differentiable? That's something you've already been tested on. Make sure you know why that is true. Statement number 2. We are told to assume that there are 2 distinct roots. This means there exist 2 different x values, a and b, such that f of a equals f of b equals 0. Okay, continuous and differentiable, endpoints are equal, so we should be able to use Rolle's theorem. So if 1 and 2 are true, then Rolle's theorem tells us there exists a number c in the open interval ab such that the derivative equals 0. So continuous, differentiable, endpoints are equal. We've already proven Rolle's theorem. So if 1 and 2 are true, then number 3 has to be true. Well, what's going to end up happening is that if we can show statement 3 is false, then either statement 1 or 2 is also false. Okay, so this is called a proof by contradiction. And let's see what happens. So we take the derivative of the function, and we get 2 minus cosine x. Rolle's theorem said that that should equal 0, but we know that 2 minus cosine x is never 0, because cosine is a number between -1 and 1. So the biggest it could be is 3, and the smallest it could be is 1. So the range of 2 minus cosine x is 1 to 3, so it's never 0. So we've shown that the then part, so the second half of Rolle's theorem, is false, right? So we're saying, we've shown that this entire statement is false, that f prime of c is not equal to 0 anywhere on the interval. Okay? So that tells us either 1 or 2 is also false. Well, we know that this is true, right? You should know why this is continuous and differentiable. That means number 2 has to be false. That means there's something here that's false. Well, we were told to assume f has 2 distinct roots. So if number 2 is false, that's the reason it's false. The assumption of 2 distinct roots is the false assumption. So f does not have 2 distinct roots. It only has 0 or 1. Right? That's the only... Well, if it doesn't have 2, it doesn't have more than 2. So the only thing left is 0 or 1. So it either doesn't cross the x-axis or it crosses exactly once. So how do we show that that function crosses at least once? How do we show it crosses one time? Well, that's where we're going to use the intermediate value theorem. Because f is continuous, the intermediate value theorem from earlier in the class gives us what we want, right? So the intermediate value theorem says if we can find 2 points with different signs, a continuous function must cross the x-axis somewhere in that interval. So I picked the 2 easiest numbers to evaluate, right? 0 and pi, right? So plug in 0 here, you get -1. Plug in pi here. Sine of pi is 0, so you get 2 pi minus 1, which is around 5.28. So because f of 0 and f of pi have different signs, there's a 0 on the interval from 0 to pi. So the function crosses the x-axis at least once. So if f crosses the x-axis at least once, and because of Rolle's theorem, can't be more than 1, it has to be at least 1, that means it's exactly 1. And we've solved the problem. So I know a lot of you coming into this class weren't expecting these sorts of problems, but this is what we do as much as we just compute derivatives, right? We use what we know about derivatives to prove more difficult or more interesting problems. So this is not algebra, right? These are proofs. All right, let's keep rolling. So now we're ready to talk about the mean value theorem. So it's similar to Rolle's theorem, continuous differentiable, but that's all we need. We don't need to know anything about the values of the endpoints. If it's continuous and differentiable, then there is a number c in the open interval, ab, such that the derivative of the function at that number is the same as the slope of the secant line, right? You'd recognize that equation, f of b minus f of a over b minus a, as basically being the slope of a line through 2 different points. So what does that look like? Well, these graphs, again, show us why it's believable, and they show us what's going on, right? Here's A, here's B. So here's your secant line. So somewhere between these endpoints, there is a tangent line where the slope of the tangent line is the same as the slope of the secant line here. So it could be more than one place, right? But this is saying continuous and differentiable means that there's at least one place. So here there's one, and here we have two. Right? Your function could look like this. Here's your secant line. There's actually two places, P1 and P2, where the slope of the tangent line is the same as that secant line. So what we're going to do is we're going to prove the mean value theorem. It's a pretty hairy proof, so you just got to strap in and hang on for, try to keep up. And then later on, we're going to use the mean value theorem to solve problems. And again, this mean value theorem is used a lot in calculus moving forward. All right. So what we're going to do is we're going to define a new function called h of x to be the difference between the function and the secant line AB. So this is just a generic picture, right? We're just saying that we know A exists, we know B exists. There's going to be some difference. So the function is the entire height off the x-axis. H, we're calling the difference between the function and the secant line value. Okay, so let's look at where this construction comes from. This thing here, okay? So this is the slope of the secant line, right? This is the equation of a line, right? This is point slope form, right? So this is basically saying, this is y. Y equals f of a plus the slope times the difference between x minus a. So as you slide down here, your your y coordinate is given by this equation. So look here, it starts at f of a. Here's your slope times the difference between x and a in the x-axis. So if we start here at a, then x equals a, and this is 0, right? Because you just have a minus a. So this is 0. So we just have the point f of a. So that checks out. What happens if we get to b? What happens if what happens if x equals b? Well, this becomes b minus a. And then we have b minus a divided by b minus a. This just goes away. So we have f of a plus f of b minus f of a. What's left over is f of b. So because this is linear, we can build an equation, right? This is just point slope form, simplified. So we know the height, and we're calling h of x f of x minus that green part. So h of x is sort of how much difference is left over. It's f of x minus the green part, which is this. And what we're going to do is we're going to apply Rolle's theorem to that h of x. Just looking at it, you might think, how can we apply Rolle's theorem to that? The endpoints aren't equal. But remember, h of x is the difference between f of x and the line. At the endpoints, the y-coordinates are equal, so we can apply Rolle's theorem. All right, so let's get going on this. So I already explained where all this stuff's coming from, but here it is visually placed out in front of you. So point slope form, we're going to derive the equation of the secant line, right? So we know the slope. So y minus f of a, remember f of a is just our known value. We could use f of b because we know both values, but let's just go from the left to the right. It doesn't make any difference which one we pick. You'd get the exact same answer. So we're just starting on the left side, saying we know a and f of a. Those are known values. So you plug them into point slope form, and then we simplify. So here, instead of saying y equals, we're just going to call it g of x. I'd rather have this than be a function because we're going to want to take some derivatives, right? So we want to have consistent notation. All right, so that's our g of x function. That wasn't labeled on the previous slide, but that's what we're calling this. This guy here, this green thing, is g of x. Now, h of x is just f of x minus g of x. So f of x is the height of the whole function. G of x is that smaller bit that goes up to the line. And h of x is the rest. Now we back substitute this value of g of x. We plug this whole thing in here to get this expression. Then we distribute the negatives. Okay, so we get a minus f of a minus here. Right, so it's a bunch of minuses. So look at what we have. We have h of x just in terms of f of x, which is what we want. Remember, f of a is a known value, a is known, b is known, and f of b is known. Those are constants. Those are known values. The only thing not known is x. So now that we check that this h of x function satisfies the three requirements of Rolle's theorem. Oh, clicked the wrong button. Is it continuous and differentiable? So that's something that you have to be able to check. Right? So why is it continuous? Why is it differentiable? Make sure you understand why that's true. So the main thing we have to check is that the endpoints are equal, that h of a equals h of b. Okay, so I want you to think about this. It's differentiable because I just showed you the derivative, right? So we just take the derivative of the function and look at what happens. This is a constant, so it's 0, so it goes away. This is a constant times x minus a. X minus a is a line, right? As a function, it's a line. The slope of a line is m. So if this is y equals mx plus b, m is 1. So when we take the derivative, it's just this times 1. So this is the derivative of h prime of x. It's the derivative of the function minus the slope of the line, which should make sense, right? Because the derivative of a line is just its slope. Now we need to check that h of a equals h of b. So let's plug in h of a. So we plug a in everywhere we see x. You get f of a here, and you get a here. This becomes 0. This becomes 0. So you have 0 minus a number times 0, which is 0. Now we check h of b. Everywhere you see an x, you plug in b. Right, so we have b minus a, so and this f of b minus f of a. So watch what happens here. This b minus a and b minus a cancels, so we have f of b minus f of a minus itself. Any number minus itself is 0. All right, so continuous, differentiable, and the endpoints are equal. So now we can use Rolle's theorem. So Rolle's theorem tells us somewhere on AB, the derivative equals 0. So all we have to do is set the derivative equal to 0 and solve for C. Right? Well, guess what? That's the mean value theorem right here. This is exactly the result of the mean value theorem, so we're done. So for those of you who are new to proofs or maybe don't like them, you're going to have to know this stuff. Go back over this until you understand it. You should be able to verify all these facts and all these proofs. There's a little bit of algebra. I show some of the algebra, but mostly you should be able to verify this stuff. So I showed most of the algebra in this one. We're not using anything fancy. We're just using plugging in numbers, canceling terms, distributing, and factoring. That's all we're using. There's no advanced algebra tricks used for any of these. All right, so the mean value theorem has been proven to be true based on Rolle's theorem, based on Fermat's theorem, and the intermediate value theorem. So now let's use the mean value theorem to work a problem and see what happens. So here's our function, f of x equals x cubed minus x. A is 0, b is 2. So what we're saying is that on the interval 0, 2, that there is a tangent line whose slope is equal to the secant line through the point a f of a, b f of b. So let's verify the conditions for the mean value theorem first. So that's a polynomial, continuous, differentiable. Right? So that's easy, right? We already proved that that's true. Next up, we want to, oh, sorry, I forgot to read part B. Sketch the graphs of f of x and the secant line. Estimate the value of c predicted by the mean value theorem. Okay, so we're looking for the point on the curve where the slope of the tangent line is equal to the slope MAB of the secant line. So here's the secant line. So instead of estimating the slope, the easiest thing to do is just draw a parallel line and see where it intersects the curve. So I don't know if you guys can see that, but there's a green parallel line. All I did is just sketched it out and moved it down. I just moved it straight down until it was tangent. So the slope is the same. And it looks like, so that's our point C, right? We're not exactly sure what that number is. We'll figure out what it is. Looks like it's about 1.1, yeah, like 1.15, a little bit less than 1.2, right? That's what I said. So it appears that the value of C predicted by the mean value theorem is a little less than 1.2. So on a test or something, I'll just ask you to estimate it. You don't have to get out a ruler and draw it by hand. Just give it a little sketch. Now we need to solve for that value, right? So continuous, differentiable is all we need. Then we need to solve. So we need to take the derivative and set it equal to the slope of the secant line. So we want to find C in the interval 0, 2 such that the derivative is equal to the slope of the secant line. So on the left side, I plug C into the derivative, and I just call it 3c squared minus 1. And then I compute the slope of the secant line, and I get 3. So 3c squared minus 1 equals 3. So 3c squared equals 4. C squared is 4/3. And so C is 2 over radical 3, which is 1.154, which is pretty much what we thought it was based on the graph. So obviously on an exam, you're going to have to calculate this. You have stuff like this on the homework. But understand that anything I go over in the class notes, you are responsible for it. This is all the same stuff in the book. I might use methods that are a little bit different, but if you use a book method, that's fine. If you use my method, that's also fine. But you can't just use stuff that, you know, your uncle told you, or your tutor, or your friend who took calculus, or your internet buddy told you. You got to use techniques either in the videos, in the textbook, in the homework, or in the notes. Have to use those techniques. Well, that's it. And I went ahead and gave you guys some more homework that I'm going to collect as part of exam 3. So they're sort of like exam questions that you have a week to work on. Or if you're waiting to the last minute to watch this video, that you have like a couple hours to work on. They're in the section 3.2 exercises. They're all proofs like the ones that we did earlier in this section. And that's it. So if you have any questions, as always, let me know. And you can post questions on the discussion forum, or email me, or come to one of the Q&A sessions when those are held. So that's it for this video. And until next time, study hard, and I'll see you next video. Bye-bye.